Hello. Good evening, everybody. Oh, the bit rate is so low. I don't know if you can see me clearly. I showed up on the screen. Good. Okay. All right. As we promised you in the mid-semester exam revision, we will do a final exam revision during the final exam period. And you can see the lighting of this room becomes much better, right? And I said, how was your long break? Sally says, sucks. No way. Look, even if it's a travel between a library and a home, it should be a good break, right? You have a rest during your travel, I suppose. Okay, anyway, now let's look at some common topics that you want to cover in today's revision class. And from the survey I had, 6 of you have replied, and let's see. Okay, look, you want to cover model, logistic regression, when to use what formula. Okay, when to use what formula. All right, regression, please. Structure of the final exam. Well, the structure of the final exam can be seen on Canvas, so don't worry. Regression and logistic regression. So I can tell the common area of difficulty is regression and logistic regression, right? So today I'll spend probably half an hour, do a quick review on the regression so that my purpose is to give you a big picture or a helicopter view of what's going on in regression analysis, okay? And also, if you have other questions, feel free to post them on here on the live chat part, okay? Yeah, I mean the part here, okay? All right. Now let's go back. Oh gosh, sorry about that. That was an accident. All right. Finally, after several months, I can see all of you behind the screen. So when we talk about regression, let's start with a very important concept. What is statistical model? Okay, so once you understand what is a statistical model, I'm pretty sure you're gonna have better understanding on no matter it is linear regression model or even ANOVA model, okay? So the statistical model, from its definition, it's a set of rules to generate whatever data, but to give you an intuitive understanding, I will explain statistical model in plain English in a very easy way. So you can regard any statistical model as a population data generating machine. So why is understanding statistical models so important? Because you get to know the statistical model are generating population data, okay? Or just data generating machine. So whenever we talk about a model, you need to write down the population things instead of the sample things. But anyway, we'll look at that later on in the real questions, okay? But now, first, we understand the model is a kind of machine. So no matter it's a ANOVA model or linear regression model, it's just a machine, right? So this is a kind of machine. And your input may be some variables, x1, x2, whatever. And after some operations, it will generate a data y. Right? So linear regression model or multiple linear regression model is a set of rule or a set of machine that generates the data like this. So it starts with a linear function, beta 0 plus beta 1 x1 plus beta 2 x2 blah blah blah, blah plus beta k xk plus epsilon. Therefore, if you are asked in the exam question, what is the multiple linear regression multiple linear regression model, right? When you are asked what is the model, then you need to write down this formula, okay? Because all of those are population parameters. This is the population intercept. This is the population slope, and all different slopes. And this is the population error term. So Tausi Stawi is asking how long will the revision session last? It's probably lasts 1 hour or 2 hours, okay? It depends on how many questions do you have. If you have too many questions, I'll probably run another one tomorrow or the day after, okay? So that's all about the statistical model, all right? And this is multiple linear regression model. And this will give you a big picture of what do you need to know regarding the multiple linear regression. And actually everything you've learned is in this equation, okay? Believe it or not. So let's see. Now, if this is the rule of generating the population data, then if we picture those data over here, well, let's suppose, even though we have multiple x, but I can't draw x1, x2, x3, so many dimensions here, right? Let's suppose this is in a k dimension space or k plus 1 dimensional space, right? And we have x1, x2, x3, so many x's. But now I will simplify it as in a two-dimensional plane or two-dimensional space. So we only have x and some y, all right? Y and some x. Therefore, this data is generated into two stages. The first stage is from this straight line equation, right? So if we ignore this error term, all right? If we ignore this error term, so only look at the left-hand side part, okay? Or we call it part 1. So it's just a straight line, right? So we call this one, or to be more precise, how do we remove this error term? Well, we know this error has a mean of 0. Therefore, we're gonna take an expectation on both sides of this equation so that we got what so-called an EY, right? Well, EY given x, given any x series, equal beta 0 plus beta 1 x1 plus beta 2 x2 plus beta k xk. So this is the first part of multiple linear regression model, okay? We can call this population straight line, right? Or population regression line, or just the population line, all right? So that's the first part in this model. And the second part in this model is this error term. This error term is assumed to be a normal distribution with mean 0 and a constant variance, sigma epsilon square, whatever, okay? So from those two steps, we can understand how the population data is generated, okay? So we start from having this straight line. Therefore, for any given x, we're going to have a EY, right? The expected value of y. For any given x, we're going to have an expected value of y. So all those expected values will form a straight line, right? So this is part 1, the straight line, okay? So this is how the data is generated from this model, first step. And the second step, we have this random error. Therefore, they are normally distributed. So therefore, for any given x, the true value of your observed y is not exactly on EY here, right? It can be above or below this. And this random error or the random variation actually follows a normal distribution with mean 0. Therefore, we have for any given x, we can observe data like this, right? Okay, so that's all about the multiple linear regression model, all right? So here, what you need to take away is that first of all, a model will generate what? Population data, right? Generates population data. Or it stands for a population, okay? So here we have population line, and we also have a population error term, okay? The first part is our population line, or population straight line, or population regression line, and the second part is our population error. So we know this error follows normal distribution. And within this population straight line, it is actually determined, we can say it's determined by all those coefficients, right? Beta 0, beta 1, beta 2, and beta k. So all of those betas are population parameters, okay? They are population parameters, all right? So why is this important to know? That's because all we are learning is trying to estimate the population regression line as well as the population error term. So all you learn in the last 3 weeks is about the estimation or other applications on those two things, okay? So now, let's have a look. If you still remember our main task of statistics, it's actually to use sample statistics to estimate population parameters, right? So the main task of statistics, it stopped, but it should be fine. The main task of statistics is to use sample statistic, okay? Use sample statistics to estimate the population parameters, right? For example, we used to learn the population parameter mu, population mean, right? And we use sample mean to estimate population mean, right? And also we learned population proportion, P, and we use sample proportion P hat to estimate the population proportion P. All right, so you can see every time we want to estimate some population stuff or population parameter, we can always find some sample things to estimate the population things, right? So here, again, in any statistical model, there are different population parameters. And the first group of population parameters actually formed this population regression line. Therefore, the most important thing here is in this estimation process, we will estimate this population line using what is called a it can be called a sample straight line, or it's called estimated regression equation. Okay, so this is called estimated regression equation. And this equation, instead of using EY given X, it's an estimated or predicted Y. So it's denoted by Y hat. And you need to know Y hat is called predicted Y value, okay? Okay, so this is called predicted Y value. Equal beta 0 hat plus beta 1 hat x1 plus blah, 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 plus beta k hat xk, no epsilon, because we are only estimating the population line, right? So we use the sampled line to estimate this population line. And you can see this is the sample intercept beta 0 hat, and this is used to estimate the population intercept beta 0, beta 1 hat, beta 1, beta k hat, beta k. Okay, so in short, in the estimation, we just take a sample from this population. So this is our population, right? So we just take a sample. For example, the sample is here. And then the first thing we're going to estimate is a line, which stands for the population expectation line, right? So we are trying to use the least square method, which is, I believe the calculation is not required, to find out this regression line, okay? And definitely this line will never be same as the true population line, right? Because just like your observed sample mean will always different from the population mean. Sample proportion will always be different from the true value of the population proportion. And also the sample straight line will always be different from the population straight line. Therefore, in your exam question, if you are asked to write down the estimated regression equation, okay, then you should write y hat plus any estimated intercept value. So all of those are values that you observe from the data, right? Or you calculated using the least square method, right? So if the question asks you to write down the estimated regression equation, you should write something like this, right? Y hat equal 46 plus 3x1 plus 6x2, this kind of things, okay? So this is the time you plug in all the numbers in, okay? All right, so that's the first thing you need to know. The difference between the sample estimated equation and the population regression equation, okay? So the population regression line is the expectation line. You probably have noticed that in your Aplia weekly homework, right? And your sampled line, it's beta 0, beta 1 hat, beta k hat, that sort of things with the real numbers. Also in your Aplia, sometimes it's B0, B1, or BK, right? It doesn't matter. It's just a notation difference. But you shouldn't use beta anymore in here. Okay, and also this one shouldn't include the error term because this is the estimation of this straight line only. Okay, so the sample line to estimate the population straight line. All right. Okay, so that's one thing. And the second thing, well, before we move on to the second thing, let's think about why do we calculate this estimated regression equation? Well, yeah, some of you got the right answer, right? So we apply this estimated regression equation by actually for prediction purpose, right? Sorry, I just finished my dinner, so my brain is not functioning very well, but we use that for prediction purposes. So now you can see once we get this equation, every time when we plug in all the numbers of x, we can predict a y value. So this is called the predicted y value, right? Okay, so this straight line is y hat, all right? Okay, secondly, as I said, there are two things we need to estimate in this linear regression model. One is the straight line part, but another equally important thing is the error term, okay? The population error term. Now, from here, we can say the difference between any observed y value and your predicted y, no, this is not predicted y, this is EY, right? Expected y value is called the error term, right? Therefore, in order to estimate that, when we come back to our small sample, I'll use another color, right? Another color should be better. So if we use a sample, we can still find this kind of difference, right? But this is not the difference between the actual y value between that population line. As we know, this line is the population line, right? But instead, we use the sample line to take this difference, okay? And we call this difference as residual. Therefore, residual, the second part, very important. The residual is generally used to determine if, Residual is used to determine, it's not at the stage of determine, but residual first is an estimation of the population error term, okay? So we call it EI, and it is calculated by the actual y value, yi, minus your predicted y value instead of the actual, the expected y value here, okay? So yi minus yi hat, and this theory is called residual. And the purpose of having the residual, it will not help that much in terms of prediction, but it actually controls the quality of the prediction. Therefore, the residual can usually be used to assess if the model is good or not, okay? It can be used to assess the model. And believe it or not, we finish everything that you have learned in multiple linear regression or simple linear regression, but without doing any detailed things, right? Those two things are actually the key thing that you learned in multiple linear regression. It forms the big picture of your of the multiple linear regression analysis. All right. So in the first 15 minutes, we covered what is statistical model. We know that it's just some population data generating machine. When you input some data and you can generate an output Y. So this is a kind of machine. And in this machine, the inputs are the X values. And then after some operations with the straight line part, and then add a random error, it will generate the population data like this, right? However, just like the population mean and population proportion, for any population parameters, we will never know its true value. So theoretically, there should be some true values, but we need to estimate them, right? So therefore, we take a sample from this population and get here, right? So this is our sample. And in this, using this sample, we can estimate both of the two parts in the population regression model. The first part is the straight line. The sample straight line or estimated regression equation is an estimation of this population expectation line. And the difference between the actual value and the y hat is the estimation of the population error term, which is the difference. Actually, the error term can be calculated by the actual y minus this EY, right? EYI given any X. Okay, so yeah. All right. Okay, so that's all about the big picture so far. And the key takeaway here is that when in the exam question, if you are asked to write down the population, write down the model, right? The multiple linear regression model, then you need to write down something like this, right? For example, cost equal beta 0 plus beta 1, number of hours plus beta 2, distance from the city, whatever, right? And don't forget to plus epsilon, because those two parts forms the whole statistical model, right? So never miss out this error term when you are asked to write down the linear regression equation, okay? Oh, sorry, write down the linear regression model. However, if you are asked to write down the regression equation or estimated regression equation, you need to find out the values of beta 0 hat, beta 1 hat, or beta k hat, and plug in all those numbers in, and finally get this estimated regression equation. All right? Okay. So that's the first thing. That's the big picture. Now let's see what kind of questions do you have. Eric Lee is asking, do you have PLG tomorrow? I don't know. Asked Algo, do we have to prepare the non-parametric statistics? Well, from my experience, I think the non-parametric statistic is not that heavily tested, but you still need to know, right? You need to know how they works. Okay, anyway, let's move on to the different topics. Okay, as I said, the estimated regression equation are for prediction purpose, and residual is for assess the model. Therefore, in the next half an hour, I'm gonna talk about in details what are the aspects you need to know and how possibly the questions can ask you in those two big topics. Okay. All right, so now let's first focus on the first part. I call it part A, okay? Part A is prediction. In terms of prediction, it is actually very simple because once you got this estimated regression equation, right? Beta 1 hat x1 plus beta 2 hat x2 plus beta k hat xk, no epsilon, right? And once you plug in all those x numbers or x values, you can calculate the y hat, right? So the prediction of the linear regression will be very easy. However, there are two concepts that are not that easy as this one. So the first concept is called confidence interval, and the other, yes, it's prediction interval. So this is confidence interval and prediction interval, all right? Okay, so for confidence interval, it actually measures it actually predicts the average, okay? It's the average y given the same features of x. But for prediction interval, it actually predicts the particular value of one particular observation. So you need to know the difference between the confidence interval and prediction interval. Okay. Well, do you know the difference between confidence and prediction interval? Can I skip this part? Because I think you should know them, right? Okay, but anyway, this is well, if you don't know, just go back and read your slides, all right? So I just let you know this is important. You need to know the difference between confidence interval and prediction interval. Particularly, you need to know the prediction interval is generally wider, okay, than the confidence interval, because when you estimate one particular observation, you tend to make a lot of mistakes, right? And also it tends to vary a lot due to their personal difference, okay? But for confidence interval, you're actually measuring the average of all observations with the same features, so it can be precise, right? Okay, so that's all about the prediction. And the most important thing I want to mention here, and this is the thing that confuse a lot of you as well, is the way to assess the model. All right, so in the way of assess the model, you basically spend a lot of weeks, probably 2 weeks, covering how to assess the model is good or not good, right? So here, I'm gonna give you a lot of 2-packs, a number of 2-packs, probably 3. And And all of those are the aspects then that the questions can ask you to answer. Okay, so to assess the model, the first two-pack that we get to know first is two-pack number 1. I tend to call it fantastic R's. Fantastic R's. Why do I call it fantastic R's? Well, I'll show you later on, right? But it's everything. But some of you, if you have reviewed this, you may have noticed it must be some R square or just the R square, something like that, right? So in the assessing the model, two-pack 1, fantastic R's, the first tool, the tool number 1, is called R squared, or it's called coefficient of determination. Okay, coefficient of determination. So if you, in your question, you're asked, what is the coefficient of determination? You need to know it's R squared, right? And it's calculated by SSR divided by SST, right? SSR stands for the total variation that is explained by the linear regression model, and SST is the total variation in Y. Therefore, another thing that you can be tested is to interpret R square, okay? So the interpretation of the R square is that whatever percent, so when you calculate the percentage of R square, whatever percent of total variation, so the key thing is you need to write down the variation here, okay? Variation is explained by the multiple linear regression model or by those independent variables, by the MLR model, okay? So that's the interpretation of R square, all right? So that's all you need to know about R square. Okay, secondly, the second thing compared to R square, well, multiple R. Well, multiple R is just the square root of R square, or just R itself, okay? However, most of the students will lose mark on R square because they don't know the meaning of, multiple R. They don't know the meaning of multiple R. Therefore, if you read these notes 3 hours or just 10 minutes before your final exam, you can probably get 2 more marks, right? Why is that? Because many times, the question tends to ask you, what is the correlation between Y and Y hat? And then you need to know it is multiple R, all right? Therefore, multiple R also stands for the correlation. Yes, Changxu, you are right. So the correlation between Y and Y hat is multiple R, okay? So don't lose mark on this, all right? And more specifically, in simple linear regression model, okay? Only in simple linear regression model. I think this also happened in your slides, right? In simple linear regression model, the correlation between X and Y can be described or can be determined by plus or minus the square root of R square, or positive or negative multiple R. This is because the Y and Y hat's correlation is R, but X and Y can have positive or negative correlations, right? It depends on whether beta 1 is whatever, right? It's positive or negative. Therefore, the correlation between X and Y can be positive or negative multiple R. So you need to pay attention to this if it is a simple linear regression question, okay? All right, so that's all about multiple R and how can multiple R be tested. So we have 2 R's altogether now. The third R, okay, the third tool in this two-pack, number 1, is called adjusted R square. Well, a common problem in R square is that whenever you add in more independent variables, the SSR will always increase, and if SST remain unchanged, the R square will always increase. If that is the case, the best model determined by R square will be a model that includes everything in the world, because no matter how important the independent variable is, as long as we add in more independent variables, then SSR will definitely increase, so R square will always increase, all right? Therefore, to avoid this kind of to avoid this kind of mistake, right? So we tend to calculate adjusted R square, and this adjusted R square is adjusted by the sample size as well as the number of independent variables. Therefore, it is calculated by 1 minus SSE divided by the degree freedom n minus k minus 1, and then divided by SST divided by its own degree freedom n minus 1. All right, so this is how we deal with the adjusted R square. And in terms of the understanding of adjusted R square, we only need to know adjusted R square has adjusted this R square for the sample size n, right? So the sample size is adjusted, from sample size perspective, but also the number of independent variables. The number of independent variables. Okay, so this is the third tool in this tool pack. All right, we have R square, which is called coefficient of determination, and adjusted R square is called the adjusted coefficient of determination. And the last thing in this tool pack is called the standard error of estimate. This is also very important because many times the question asks you something, but you don't know what it is asking you. All right, so let's see, standard error of estimate. This standard error of estimate is actually also in your Excel output, right? In the first table, the last line is the standard error of estimate. So the standard error of estimate is actually calculated by the square root of MSE. So it's just stands for the the standard deviation of the residual, okay? Because we know that SSE is calculated by the residual sum of square. It's yi minus yi hat. This is just the residual, right? So we square it and take the sum of it, right? So if we calculate MSE, it's pretty much like we divide the SSE by its degree of freedom. So MSE is the variance of residual. So it divided by n minus k minus 1, which is yi minus yi hat square. So this is MSE, which is the variance of the residual. Therefore, the standard error of the estimate, or standard error, is the standard deviation of the residual, okay? So why is this so important? Because many times the question tend to ask you, what is the estimation, okay? What is the estimate of the standard deviation, right? Standard deviation of the error term. Well, hopefully you still remember the error term, right? The error term is this, right? And the error term is assumed to be following normal distribution with mean 0 and some variance here. Therefore, it is just asking you what is the estimation of this population variance, all right? Therefore, this variance, okay, like this variance can be estimated by our sample residual variance, right? Because this is the population error variance and this is the sample residual variance, okay? Therefore, if you're asked this question in your final exam, you need to write down the standard error of estimate, right? So it's just the sigma epsilon hat, which is equal to square root of MSE, all right? And again, the question can change to what is the estimate of the variance of the error term, okay? So if the question asks you what is the variance, the estimation of the variance of the error term, then you're gonna answer what? MSE, right? So the sigma hat epsilon square is MSE. Okay? All right. So all of those criteria are able to help us to assess the model, whether the model is good or not, okay? So if I draw two samples in two different group of data, so one group of data is like this, well, let's make it worse, okay? So one group of data is like this, but in the other group of data, or in another model, we can have the observations like this. So which one do you think is important? Which one do you think is better in terms of the prediction precisions? Definitely the second one is better, right? Oops, sorry guys. The Wi-Fi connection was somehow disconnected, so this is out of my control, okay? Yeah, I know the connection is terrible, but sorry about that. Yeah, this is our university Wi-Fi, okay? This is university Wi-Fi, so don't blame me, blame our university, okay? All right, let's come back. It's not gone. Let's come back, okay? I'm asking you which one do you think has a higher R square and which one has a lower R square? Yeah, definitely. This one has a higher R square and this one has a lower R square. In terms of multiple R, same, right? Because multiple R is just a square root of R square. Therefore, higher R square, higher multiple R, right? And for adjusted R square, well, it really depends because this is just simple linear regression, right? For multiple linear regression, usually if that is the difference, then this one definitely have a higher adjusted R square, right? This one has a lower adjusted R square. And for the fourth one, standard error. So standard error is just the standard deviation of the residuals. So by looking at the width, you can see this one's residual has a super large variance, right? Definitely this one has a higher standard error and this one has a lower standard error. So you can see the first two pack, our fantastic R's, can help us assess whether or not the prediction is precise, right? Because if the prediction is precise, we're gonna have a higher R square because the model interpret the most of the variation in Y, and the lower standard error because this will result in a lower standard error in your prediction. And vice versa. If the model is not good fit on the data, then R square will be lower because it didn't explain much in the variation in Y. so that you're gonna have a larger standard error in your estimation. Okay, so that's all about the first tool pack. Okay, so there are 4 tools in those 2 packs. 2 pack 1 R squared, 2 pack 2 multiple R, tool number 2, tool 3 adjusted R squared, and tool 4 standard error of the estimate. So if you are happy with this 2 pack, okay, so we'll just pack it up, okay, and it's all yours, okay, catch, okay, I'll throw it to you, 3, 2, 1, catch, okay, yes, so take it home with you. Take the first 2 pack, okay, now 2 pack number 2. So the 2 pack number 2, it's the statistical tests, okay, or significance test, whatever. Well, the statistical tests are also very important in assessing our model, especially how significant the linear relationship is. Okay, so for the statistical tests, we usually test the following 3 things. The first thing is the testing for the correlations. We require, if we want to perform a linear regression analysis, we need to have y and x has a strong, or at least not so weak linear relationship, right? Therefore, it's essential to test the correlation between y and x. So, this correlation can be tested in 2 ways. One is called the Pearson correlation, right? And you also learned Spearman correlation. Okay, Pearson correlation, Spearman correlation. And the only difference is that Pearson is parametric and Spearman is non-parametric. Okay, so for the non-parametric test, they use the rank of the data. Yes, hopefully you all know it. Okay. Otherwise, I'm afraid you're gonna fail this unit, right? No, I'm not saying that. Okay. Well, Pearson correlation, null hypothesis and alternative hypothesis. Rho equal 0 and rho not equal 0, or greater 0, less than 0. It depends on whether you want to test if the correlation is significantly larger or smaller or not equal to 0, right? And the test statistic, I can't remember exactly, but the t statistic is given by the observed R. R is the sample correlation, okay? Sample correlation. Rho is population correlation. So sample correlation minus your hypothesized correlation divided by 1 minus R squared, but I can't remember, okay? It follows a t distribution with the degree freedom of n minus 1, I suppose. I don't know, but yeah, just go back and look at your paper, your formula sheet or your slides, okay? So just get to know everything about the correlation test as well as the Spearman correlation test, all right? So you probably be asked test the correlation between 2 variables, and it can be rho equals 0, not 0, it can be other values. For example, if I want to see if the correlation is greater than 0.5, right? So the rho can also be 0.5 and alternative is rho greater than 0.5, so that this becomes a one-tailed test, and you plug in R, which is your observed sample correlation minus that rho is 0.5 in the null hypothesis. okay? But anyway, the first test is the testing on the correlations, okay? So this is something you need to know. All right. And also, as I said, this is used to assess the model. If the correlation is big, then we can perform a linear regression analysis, right? Because this usually happens before we perform a linear regression analysis. If there is proved to be no correlation, there's no point for us to continue working on the multiple linear regression analysis, okay? So testing on the correlations, very important. Secondly, once we construct the model and finish the estimation, we want to test if the model is overall significant. So the second tool, well, this is a tool pack, right? The first tool is correlation test. The second tool is called overall significance, F or T test. Yes, F test, okay? Because the overall significance F test is to test whether there exists some relationship between y and each independent variables so that the model is overall significant. The null hypothesis is, well, please pay attention. It's very easy to make mistake here, okay? The null hypothesis is beta 1 plus beta 2, equal beta 2 equal beta 3 equal beta k equal 0. So there's no beta 0 here, okay? We only look at the slope terms, okay? All the slope coefficients, whether all of those equal 0. And the alternative is at least 1 beta I is not 0, right? So this is overall significance test. And some of you have mentioned you can observe that from this ANOVA table in your Excel output, right? As you don't have Excel access in your final exam, so all the output, or at least part of the output, will be given, all right? And the test statistic F statistic is calculated by MSR over MSE, okay? And it follows the F distribution with the MSR's degree freedom K and MSE's degree freedom N minus K minus 1, all right? So that's all about overall significance F test. So we reject the null hypothesis if your observed F is greater than the critical value or the p-value is less than alpha, right? Okay, but in both of the way, you can determine whether you're going to reject or not reject the null hypothesis. So F0 means F observed F, okay? I tend to use observed F here. Okay, or F statistic. All right, so when we talk about the overall significance F test, let's do a quick review together, okay? Let's quick review together on the ANOVA table, because in that ANOVA table, you can be given some blanks and you're asked to fill in the blanks, right? Therefore, we need to be able to reconstruct the whole ANOVA table. So we need to get to know there are three sources of variations. The first source is the regression, and the second source comes from the residual, and the third source is the total variation in y, right? So regression, residual, and total. So in that table, the easiest thing to find out are the degree of freedoms. So the regression degree freedom is K. Please pay attention. This degree freedom is different from the ANOVA model, right? Where in ANOVA model, the SSR's degree freedom is K minus 1, but in multiple linear regression, it is K, okay? And also for the residual degree freedom, it's N minus K minus 1, but in ANOVA, it's N minus K. And for total variation, it's n-1 because it's just a sample variance of y, right? So the degree of freedom is n-1. The second column is asking us the sum of squares. So the sum of squares of regression is SSR, right? So SSR, well, you probably don't need to memorize the formula, but you need to at least know what SSR stands for, right? So SSR is the total variation explained by the model. So when talk about explain, it should be the y hat variates, how y hat variates from y bar, right? So yi hat minus y bar, it's SSR, sum of square. And then SSE is the residual sum of square. So it's the actual y minus y hat square. And SST easy, it's simply the total variation. So the total, it's the y, the actual y minus its mean y bar. Okay, so those are the sum of squares that you need to know. But I don't think you are asked to calculate SSR, SSE, and SST, but you need to know the relationship SST equal SSR plus SSE, right? Okay, so that's the first column, the sum of squares and degree of freedom. And the next column is our mean square. The mean square is just to take an average on the sum of square, and then we call it mean square. By taking average, we divide every sum of square by this k, by the degree of freedom, right? So the MSR will be given by the SSR divided by the degree of freedom k, and MSE will be given by the SSE divided by the degree of freedom n minus k minus 1. All right. And well, if you want to create something called MST, you can do that. It's SST divided by n minus 1. Well, this is just the sample variance of y, right? Because this is sum of square of y, and this is n minus 1, so it's just a sample variance. So that's why this table is called analysis of variance, right? ANOVA. ANOVA, in short, is called analysis of variance. So these mean squares are actually called variances because they are calculated by the sum of square divided by its own degree of freedom, or it's divided by the number of observations, right? By taking average. So the mean squares are the variances, okay? And they are the measurements of the average variation. Okay. Once we got to know the mean squares, then the F statistic is very easy to calculate. The F is calculated by MSR divided by MSE because we want to see if MSR is significantly larger than MSE. Therefore, we expect a large F value. So it's a one-tailed test, okay? So overall significance F test is a one-tailed test. And the last column is called significance F, or just p-value. And you know, the p-value can be calculated by F distribution right tail or whatever by plugging this number into your Excel formula, but you're not gonna be testing on anything like Excel, right? So hopefully you'll be given p-value. And it can never be done from the statistical table, so you'll definitely be given the p-value. Okay, so that's all about the overall significance F test. You need to know their null and alternative hypothesis. And make sure you're making hypotheses on betas instead of beta heads, okay? So every simple mistake can make you lose mark in your final exam, okay? So you need to write exactly the same format as this one in your final exam to get full mark, and also how do you calculate the F statistics and what are your decision rules. So critical value can be easily found in the F tables, right? So once you fix your significance level, alpha, then you can find in the F table the certain degree freedom and within a certain column, right? So it's not that hard. Okay, so that's all about the second tool in the second tool pack. And now here comes the last tool. We have tool 1, tool 2, and the last tool is, have a guess, what is it? We just finished overall significance F test, so the next should be called, yes, it's called individual significance t-test. Cool. Individual significance t-test. So for this individual significance t-test, it happens when we reject the null hypothesis. If we reject the null hypothesis in the overall significant t-test, it means overall the model is significant, right? But we don't know. We know at least one beta I is not zero, but we're not pretty sure which of the beta is not zero, right? Therefore, we are gonna talk about individual significance t-test. By performing individual significance t-test, we can determine if any single independent variables is significant or not. Therefore, the null hypothesis and alternative hypothesis are beta I. I can be any I from 1 to k equals 0, or sometimes if Boris is too bad, he may ask you to test whether beta I is equal 1 or greater than 1 or whatever, right? So please read the question carefully, all right? And beta I not equal 0 or greater 0, less than 0, or any other values, okay? But usually it's 0. And the test statistic T is given by your beta I hat, which is the value you estimated, minus your null hypothesis value, beta I. So, beta I, if beta I is 0, it's just 0, so it's just beta I hat, right? But if it is not 0, you need to plug in different numbers here, okay? And then divided by the standard error of beta I hat. The standard error of beta I hat, you are given the formula in one page on your slides, but I believe you're not required to know it, okay? So the standard error will also be given in the Excel output, right? So this follows T distribution with a degree freedom n minus k minus 1. So it's the same as the residual degree freedom, all right? Once again, the decision rule is reject the null hypothesis if, it depends on whether it is a one-tail or two-tail test, right? So for the critical value approach, usually it's when the T observed value is greater than the T critical, right? So critical value can also be found in a statistical table given certain alpha. This is for two-tail test. And one-tail test, you can write it down together with me and just try to see if you still remember the hypothesis testing, right? If it is one-tail, right upper tail, if it is greater than something, then we're going to have whether the observed value is greater than the critical value, the positive critical value, right? T alpha is T alpha. Here it should be T half of alpha, right? And if it is, this is upper tail, and if it is lower tail, it's going to be observed value less than minus T alpha, okay? So yeah, but anyway, this is your hypothesis testing contents. So hopefully you're already very happy with those hypothesis testing stuff, all right? Okay. The easier way of determining whether to reject the null hypothesis. Oh, the lights turned off. Sorry. I need to move around and turn on the light. Okay, I had a dance, so the lights turn back on. Okay. Again, if it is p-value approach, we're going to reject the null hypothesis if the p-value is less than alpha. So this is super easy, right? P-value less than alpha, we will always reject the null hypothesis. Okay, so for the individual significance t-test, it can help us determine which of the independent variables are important and which are not important, right? So this will help us determine in our final model what should be our most appropriate group of independent variables to have in our final statistical model, right? So this is individual significance t-test, and you also learned which is called stepwise regression, right? Stepwise regression will consider individual significance as one of their criteria to add in or remove any independent variables, right? Okay, so those are the first, second, and the third tool in this tool pack. But I suddenly remember you learned another significance test, which is called partial f-test. Do you remember? Yeah, so let's just add in one more tool in this tool pack, which is called partial f-test. Okay, so the partial f-test is the only test that cannot be done using Excel, okay? So you have to solve that using your hands. So you need to perform your hand calculations, okay? So the partial f-test is there to determine if you can reduce your full model to the reduced model. So you just make a choice between your full model, which is y equal beta 0 plus beta 1 x1 blah 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 plus beta k xk plus epsilon. This is our full model. And your reduced model is when you remove all the independent variables, for example, till p, okay? So we have y equal beta 0 plus beta 1 x1 blah 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 plus beta p xp. So in this model, we do have beta p xp. We also have p plus 1, p plus 2. So this one is longer, okay? Can you assume this one is longer because it stopped at p, all right? So this one is less than the full model, the number of independent variables. Okay, so we want to make a choice between the full model and the reduced model, and we want to say if the full model can be reduced to the reduced model. Therefore, the partial f-test, you need to be able to solve it starting from the null hypothesis and the alternative hypothesis. The null hypothesis is that all the independent variables that you removed from your full model, the coefficients equal 0. So it starts from beta p plus 1 equal beta p plus 2 equal beta k, okay? So from p plus 1, p plus 2 to beta k all equals 0. And the alternative is at least one of this beta I, again, not equal 0, okay? So many students tend to misunderstand the partial f-test, and they still do null hypothesis as beta 1 equal beta 2, beta equal beta k equals 0. That is incorrect, okay? So we want to test if the independent variables, the coefficient of the independent variable that we dropped from the full model equals 0, okay? So if they equal 0, it means we can reduce the model to this reduced model, right? And if not, we need to use this full model. Okay, so the test statistic, the partial f, is calculated by the SSR of the full model minus the SSR of the reduced model, and then minus the difference in the number of independent variables, k minus p, right? And then divided that by the full model's SSE. Full model's SSE divided by n minus k minus 1. Or it can also be calculated by the SSE of the reduced model minus the SSE of the full model, and then divided by k minus p, and then divided by same thing, SSE f divided by n minus k minus 1. So you can see they are the same, right? Because the difference in SSR will be the same as the difference in SSE. Because when SSR increase, SSE decrease with the same amount. Therefore, the difference will be the same. So in your formula sheet, hopefully you can see one of those two formulas and they are equivalent. And also, this will follow a F distribution with a degree freedom k minus p as well as n minus k minus 1. And also we want to see if the numerator is significantly larger than the denominator, therefore it is a one-tailed test. So we reject the null hypothesis if if your f observed value of f is greater than the critical value, fk minus p and minus k minus 1 alpha, right? It's a one-tailed test. Or reject the null hypothesis if the p value is what? Is less than alpha. Okay? Good. Yes, so Sally Ma is asking, reject null hypothesis means full model cannot be reduced? Yes, you are right. At least the full model cannot be reduced to that reduced model because those betas, those corresponding x are still important in explaining the y. Okay, so yeah, if we reject the null hypothesis, it means we're gonna prefer the full model, right? And if we do not reject the null hypothesis, it means the model can be reduced to the reduced model because all those coefficients are 0, right? So we can just reduce to the reduced model. Thank you for your question, Sally Ma. Okay, and again, the conclusion is whether we can reduce the model or not reduce the model, right? Based on what Sally Ma is saying, okay? All right, so far, I believe that's all about the tools in our second tool pack. I promise you guys, there are only 3 tool packs, okay? So later on, we're gonna deal with our last tool pack, all right? So tool pack 2, statistical tests. We're gonna test on the correlations. We can test on the overall significance using F-test. We're gonna have individual significance t-test. And finally, we're gonna have a partial F-test, okay? The partial F-test. All right, so if you're happy with this tool pack, I will pack this tool for all of you. All right, so please catch. 3, 2, 1. Okay, good. Well, Xuewen Liao is asking, do we need to explain when beta 0 is insignificant? Well, if you are asked, then you can explain, okay? If you are not asked, then just don't bother, right? Okay, so far that's all about the first tool and the second tool and the last tool pack. Tool pack number 3. Well, Qi Jieding is asking, are we required to interpret the full procedure of stepwise regression? Well, you need to know it, right? But it's I don't think it's likely to happen, but everything is possible to happen, right? If you want to get full mark, you should definitely focus. You definitely know everything, right? And if you want just get a pass, then you can discard any part that you find difficult, right? Or you don't want to do review on. Okay. Oh, there's a dark point here. Sorry about that. This is my mobile phone, and I do want to turn on the flashlight, but once I turn it on, it will stop live streaming. So I tried, but I failed. Okay. All right. But anyway, let's focus on our last two-pack. Two-pack number 3. It's called model assumptions. Once again, we need to know all the model assumptions as well in your final exams. And it's an essential part because if the assumptions are not held, we can't really do that prediction. So let me give you an easy example. Let's say if we perform a linear regression on this group of data, so definitely we can see a quadratic relationship in this data, right? But we still use a straight line. So do you think this is precise in terms of doing any prediction? Definitely not, right? So if you predict an x value even here, it will be biased. And if you predict it here, it will be, okay, the difference will be much larger. Therefore, the assumptions are also very important. So before we move on to the methods of checking the assumptions, let's go back and see what are the model assumptions on this error term and all other things, okay? So in this statistical model, as I said, it is a rule of generating data, right? So if it is a set of rules, there must be some underlying assumptions, like any restrictions on those data inputs. Therefore, there are two parts in this model, and the assumptions are also from those two aspects. And there's one assumption on this part, the straight line part, and several assumptions on the error term parts. So we will focus on both of those two aspects right now. So aspect A is what is that? It's the assumptions on the straight line. Okay, so assumptions on the population straight line. Okay, I'll just draw a line. Okay, draw the population equation, and there's only one assumption on that, which is no multicollinearity, right? Which means the correlation between any x should be equal 0, like no correlation between any x. The independent variable should be should not be correlated. All right. And you've learned two different ways to assess whether the correlation exists between independent variables. The first method you learned, or the first tool you learned, is the correlation matrix. Okay, so the correlation matrix is something like this, right? It will give you the correlation between y and x1, x2, x1, x2, x3, x4, whatever, right? And please pay attention. If you are going to determine if the correlation exists or not, we shouldn't look at the y column, right? Because y is the dependent variable, and we expect a higher correlation between x and y. So this is the correlation between x and y, all right? So for multicollinearity, it means the independent variables should have a correlation of 0. So we're going to be looking at those values, all right? So if you observe any correlation between 2x is larger than 0.9, we can say the multicollinearity is likely to exist, right? Or possible multicollinearity. Well, as I said, if you forget how to spell this, you know what to do, right? You got a multicollinearity. So here's a P, here's an I. Look, multicollinearity. So your marker will understand and give you 0 mark. Okay, no way. Okay, so possible multicollinearity. And if you observe rho that is greater than 0.95, this means what? It's very likely to exist, right? So it's called what? It's very likely, okay? A multicollinearity. Okay, very likely that the multicollinearity exists. So I'll make it a sentence. It is, right? It is very likely that a multicollinearity exists. Okay, so that's all about the correlation matrix method. And the second method you learned is called variance inflation factor, VIF. So VIF, I don't know if you really cover this in much details, but yeah, it's better than not know it, right? So VIF is actually computed by the different R squares. So what we do is to regress any particular Rx, for example, x1 equal beta 0 plus beta 2 x2 plus beta k xk plus epsilon. So we do a regression on any of the x against all other independent variables and see the correlation, okay? And we also do the same thing to x2, beta 0 plus beta 1, x1 plus beta 3 x3, so there's no beta 2, right? And then plus beta k xk plus epsilon. And then we do any of them for xi and xk, do the same thing, all right? And if we run the regression on each of those models, we can get a R square. So the first R square is called R1 square, the second R square is called R2 square, and the ith R square is called, have a guess, what is called? Yes, clever, it's Ri square. And what is called the case? Yes, the Rk square. Yes, so clever. Yes, so R1 square, R2 square, Ri square, Rk square. So you got k different R squares. And VIFI is defined to be 1 divided by 1 minus Ri square. Okay, so this is VIF. Okay, VIF. 1 minus Ri square. So in each of the model, if there are k independent variables, we can calculate k different VIFs, right? So the decision rule is if the largest VIF, okay, the largest VIF, I can say, okay, the max VIF among 1 to k is greater than 5, then it's possible, right? Possible multicollinearity. And if the max VIF among all the VIFs from 1 to k, you know what I mean, right? Probably the question is going to give you the full list of VIFs, and then you're going to determine if multicollinearity exists. So if it is greater than 10, then it's the multicollinearity is very likely to happen or to exist, right? Okay, so they are actually two equivalent methods because R, as I said, can be considered as correlation, right? So it's correlation. Therefore, if the correlation greater than 0.9, you can see 0.9 squared is 0.81. So 0.8, 1 minus 0.8 is 0.2, 1 over 0.2 is 5, right? So if correlation greater than 0.9, then the VRF tend to greater than 5. And also, if it is greater than 0.95, and you can see 95 times 95 square is 0.9, right? So 1 minus 0.9 is 0.1. 1 over 0.1, 10. Okay, so you can see greater than 0.95 equivalent to VRF greater than 10. So they are equivalent two measures in terms of I mean, they're not exactly the same, but very similar measurements on the multicollinearity. Okay, so that's the first tool on the model assumptions, and we already finished assumptions on the straight line. Okay, the part one straight line. Okay, now in terms of the error term, there is also one assumption, but we tend to break it down in multiple. So I'll write it down over here. So B, assumptions on the error terms. Okay, so in our statistical model, I mean in our multiple linear regression model, the error term is assumed to follow a normal distribution with a mean 0 and the variance of sigma epsilon square. And all of the different epsilon i's for any given x should be independent and identically distributed. So IID, later on you will know IID stands for independent and identically distributed. Okay, independent and identically distributed. So now let's look at the assumption here. In your textbook or in your slide, it actually breaks down this assumption into 4 different aspects. So the first aspect is this N, normality. So we require that all the error terms should follow a normal distribution. Therefore, we need to look at if our residuals follows normal distribution, because residuals is the estimation of the population error term. Do you remember that? Yeah, hopefully in our first page, we get to know that our sample estimated equation is the estimation of the population regression equation, and the sample residual is the estimation of the population error term. So residual is the estimation of error term. Therefore, to assess the model assumptions, we can say if the residual follow a number of patterns so that the assumptions on the error term will be satisfied or not. Okay, so normality. So in order to test normality, we're going to test the normality on the residuals. And we can look at the histogram, right? We can do a residual histogram and see it follows normal distribution. Or we can also look at a normal probability plot or QQ plot in your Excel output. But all of those are too subjective, right? So therefore, the normality is usually be tested by chi-square test for normality. So if you got assignment, right, and you want to test the normality of the error term, you need to find out the residuals list, right? You have a list of residuals and you perform a normal chi-square test for normality on these residuals. Okay, so normality. Okay, the second assumption and the third assumption, I'll put the second and third assumption together because both of them can be checked by the residual plot, right? So the second assumption requires that the mean of the epsilon, the error term, given any x, should equal 0. Oh, I'm a little bit thirsty. Let me drink something. Okay. So, we require that the expected value of the error term given any x. So please pay attention. This is a conditional mean equals 0, okay? Because many of you have the confusion. When you calculate the average on the residual, some of you just do an average and then input all these residuals, and you will definitely get a 0 value because residuals average or residual sum is always 0 for least square method. However, is it always 0? Probably not, right? But anyway, no matter whether it is 0 or not, I'm not pretty sure, but you can double check it. But it's not conditional average, okay? Conditional average means for any given x value, the error term, or you observe the residual, should have a mean of 0. So this means the residual should be looking like this. Because for any x values, and this is residual against x, for any x values, you can see the average is roughly 0 because all those residuals are around the x line, right? So this is how we check whether the second assumption is held, the mean 0, okay? And if this assumption is violated, you may observe something like this. Some nonlinear relationships, for example, quadratic. This one definitely didn't follow this assumption, right? Because you can see for this, any given x value, some of the means are positive. Look at the mean positive, but here the mean start to be negative, 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 positive, 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 right? Therefore, you can see that the values of residual has a correlation with x, right? Therefore, the conditional mean of this residual is not always 0, all right? Well, this can also be explained in words. There shouldn't be any correlation between the error term and the independent variables, right? No correlation between error term and independent variables. By checking this, we're going to look at the conditional means, right? Whether the conditional means are always 0, okay? And the third assumption, equivariance, it's also called homoscedasticity. Oh my God, I still remember how to spell this, right? Homo, means same, like homosexual stuff, right? Homo means same. And scedasticity means variance. So homoscedasticity means same variance, all right? And again, it requires all the variance of epsilon given x equal the same variance. So the variance should be the same, all right? Therefore, the ideal thing is still observed to be this. No pattern should be observed, right? And if this assumption is violated, you should observe some residuals like this. So residual against x, right? Residual against x. You may observe smaller values of the variance on residual, and then it grows bigger when x grows bigger, okay? Or the bigger variance at the beginning and then smaller, but anyway, the width will change among different x values, right? So that the error term, the variance of the error term and x are not independent, okay? And if this assumption is violated, it's called heteroscedasticity. Hetero means different, right? So this is when this assumption is violated. Heteroscedasticity. Okay? All right. So this is the assumption 2 and 3 regarding the error term. All right. And lastly, we require all these error terms are independent, right? And identically. Well, identically means all their means are zero, variances are sigma square, and all the distributions are normal, right? All of those should be identical. But the last one is independence of error. Oh, my handwriting start becoming disgusting because I don't know why, sort of tired. Independence of error, okay? Well, independence of error, this can be assessed by, when this is violated, it's called autocorrelation, right? And this autocorrelation can be detected by Durbin-Watson test. Okay, Durbin-Watson test. And for Durbin-Watson test, you know, you're going to get the D statistic equal to a value from 0 to 4, right? So 0, 2, and 4. So you're going to have different intervals. There are two critical values, DL, D lower, and D upper. And so this is 4 minus DU, 4 minus DL. And then if your D lies between DU and 4 minus DU, there's no autocorrelation, right? And if it is 0 to DL or 4 minus DL to 4, the autocorrelation exists. The autocorrelation. And if it falls in DL to DU and 4 minus DU to 4 minus DL, then we can't make any decisions. So it means inconclusive. So we don't know whether autocorrelation exists. All right. So that's basically all about the independence of error and different assumptions. Some of you is asking, how can we improve the model if the patterns can be found in the residual plot? So it varies, right? So for this one, it's easy because if the only thing we need to do is to introduce a quadratic term in your model, right? For example, beta 2x2 x1 square, right? And this can be solved. And for heteroscedasticity, you may try some log transformation, right? So if you take a log transformation on x, and this can be improved somewhat, or, well, it depends, right? So, well, it's not log transformation on x, probably log transformation on y. So if you take a log on y, then the larger values and the larger variance will be shrinkaged. Okay, so it all depends. There are several ways of dealing with those problems if you observe the residual plots like this. Okay, and I think your slides also have given you a lot of instructions, not instruction, but recommendations on how to improve your model if the model assumptions are not solid. Okay. All right. So that's basically all about the model assumptions as well. Okay. Model assumptions. We've got the model assumptions on the straight line, which is the no multicollinearity, and we're going to test it by using correlation matrix or VIF. And in terms of the assumptions on the error term, we break it down into 4 different aspects. So this is aspect 4, right? 4 aspects: normality, 2 and 3, linearity, and homoscedasticity, and finally independence of error. And we know how to test each of the assumptions as well. And finally, there's one more thing in the survey that you want to cover, which is the logistic regression. Well, actually, logistic regression is not hard at all if you really understand what's going on in logistic regression. So previously, you can see in our y variables, all of our variables are numerical or categorical. Yes, our y values are usually numerical in linear regression. So it can be salary, it can be sales, it can be cost, it can be anything that is numerical. However, what if I want to determine if something will happen or not? So that's a categorical thing, right? So logistic regression will happen if your y is a binary variable, which means it can only take two values. One is success, another is not success. So logistic regression is actually to help you assess whether y will happen or will not happen, okay? So this is applied widely in the credit card default detection, okay? Credit card default. Because the result can be default or not default. So your prediction will be default and not default, right? So if 1 stands for default and 0 stands for not default, then we can do a regression on that. However, let's see, if we directly use y equal beta 0 plus beta 1 x1 blah, 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 plus beta k xk plus epsilon, this kind of model, is it feasible? Not really, because it's very easily we can predict a y to be like 1.5 or 0.6 or -3. So it doesn't make sense because y's input are just 0 and 1s. Therefore, we cannot directly use the 0 and 1, right? So instead of using y directly, we use the probability of default and the probability of not default, okay? So this is the probability, and this is going to be the 1 minus the probability, or Q, right? So if we do a regression on the probability, let's see if it becomes better, all right? Because the probability of default, if default happens, it's definitely 1, right? So it's still 0 and 1. However, it's very easy to predict a probability to be 1.3 or -6, 0.6, and then we will never know how to explain those results, right? So probability, we still can't directly use the probability, right? So instead of using probability, we take one step further, we construct a new value called odds ratio. So if you have ever gambled, I never done that, but if you go to any casino and do some gambling, there are odds ratios, right? And the money that you are paid will based on those odds, right? So the R is defined to be the probability of success or default divided by the probability of not success or not default. In that way, this is the data range from 0 to 1, and this becomes a data range from 0 to positive infinity, because when this is 1, this is 0. So 1 divided by 0 is infinity. However, it's still problematic. So if we regress this R here, let's see what we can get. if we regress the R here, we can still predict something that is negative 0.6, right? So if we reduce, we have a negative 0.6, then how do we calculate the probability? So we still can't directly use odds ratio, right? Okay, fine. Let's take the final one step further. We're gonna do some transformation on the odds ratio so that we can make the range to be minus infinity to positive infinity. The transformation that we're going to use is the logistic function, because the logistic function has the feature, hopefully you still remember it from your high school, okay? The logistic function, the x value ranges from 0 to infinity, but y value ranges from minus infinity to positive infinity. Therefore, we take a nature log of r, the nature log of r as our odds ratio, and substitute. Okay, finally, we find out one good thing to become our dependent variable, right? So still use this regression model, and we use log of r. Okay, so the log of r becomes beta 0 plus beta 1x1 plus beta k xk plus epsilon, and this is called logistic regression model. Okay, so this is logistic regression model. Okay, so hopefully by this illustration, you get to know why we do this kind of things, okay? We're just trying to convert this binary independent variable into a continuous numerical, and the range is negative infinity to positive infinity, so that we can always return back a valid prediction, okay? So that's all about the logistic regression model. And the good thing is you are not required to know how to estimate that logistic regression, because we, instead of use ordinary least square method, we use maximum likelihood method. And this is beyond the scope of this unit, so don't worry about that. So the question will be much easier because you'll be given all the beta hats, beta 1 hat, beta 2 hat, and so on, beta k hat. And all you need to do is to predict, to write down the estimated equation, which is log r hat equal beta 0 hat plus beta 1 hat x1 plus beta 2 hat x2 plus plus beta k hat xk. So you're gonna plug in the real independent variables and the real numbers in here, okay? And finally, you need to determine if somebody's income is whatever, saving is whatever, education is what level, and then you're asked to predict whether this person will default or not default. Okay, so for example, you plug in all those numbers and get the log of r hat equal say 0.3, okay? So if you got the log of r hat equals 0.3, then you can always work out r hat, right? How? So r hat equal e to the power of 0.3, is that right? So e to the power of 0.3. So once you calculate r hat, you know r hat is calculated by the p hat divided by 1 minus p hat, because this is how is that defined, right? So p hat divided p hat, so by solving this p hat, let's do it quickly, r1 plus stuff, right? Yeah, it becomes r hat divided by 1 plus r hat, right? And then you can get a probability. So if it is greater than 0.5, we will predict this person as default. If it is less than 0.5, we will predict this person to be not default. Okay? All right. Also, you can choose other threshold. It can be 0.5, or if you want to be more conservative, you want to set 0.3. Right, as long as greater than 0.3, we will not issue the credit card to them because they're gonna default. Okay, so that sort of thing. Therefore, it's all about the calculation stuff, and so you can see the logistic regression It's not that hard, right? And if you want to know example of the logistic regression, I can give you a link of last year's final exam consultation, and I believe in that one we have a example of logistic regression. Okay, and yeah, it's not hard, right? And you also have an example in your practice question, I guess, the past exam 2015 semester 1 paper, right? So just do that. Okay, now let's start answering some of your questions now. Yeah, Girasol W is asking, how can we improve the model if the patterns... Oh yeah, I already answered that. Okay, right. Okay, so far, that's all about what you put in your survey. Okay, so in that survey, you mentioned model, logistic regression, regression please, regression and logistic regression, and we finish all the regression part. Any other questions? Any other questions? I suppose you haven't started reviewing this unit, right? Because this exam is going to happen next week. And as we can see, no more than 60% is watching. This means most of them wanted to watch the recordings instead of watch it on live, right? So you are early birds. You start preparing this so early. So I wish you all to get a high distinction in your final exam. Okay, thank you very much for your watching. If you don't have any other questions, we will call it a day. Okay, and if you do have other questions, and you urgently want me to hold another consultation, I can probably do another one before your final exam, okay? Oh, Hailey Zhang is asking, I'm wondering the what? Okay, I know you want to ask a question, okay? Yeah, please finish typing it, okay? I'm wondering the oh gosh, what's your question? Hello, what's your question? Hi, Li Zhang. Confidence interval template. Well, there's no templates in answering the questions. You just write down the formula and plug in the numbers and done, right? There's no templates, okay? Parametric and non-parametric tests. Yeah, probably. Yeah, we can consider that. Yeah, sure. For estimating P or sum. Yeah, I mean, estimating P. Well, for estimating P, it's P hat plus or minus Z half an alpha times P hat times 1 minus P hat divided by N, right? And you just state, for example, the formula is this, and P hat is, you calculate, and you find the Z value is what, and the N is equal what, so the confidence interval is calculated to be what. Okay, so that's basically how you calculate or how to present your answer in your final exam. Okay, so it's not that strict. Well, Qijie Ding is asking, is the epsilon only for the population perspective and residual for the sample perspective? You are absolutely correct. Epsilon is called population error term, right? And for the residuals, it's the observed error term from our sample, okay? So it's E, and this is error term. Sharon Yan, I'm wondering, do we need to remember the formula that is not contained in the formula sheet? I don't think so, but I don't know what's gonna happen in your final exam. But if I were you to prepare the final, given the limited amount of time, I will ignore the formulas that are not on the formula sheet from the exam preparation perspective, but it doesn't mean they are not important, okay? Those contents, you may still need to understand them, okay? Mitali Gupta is asking, can we have some practice example questions? Yeah, I think I can post, the example question, I don't have any other questions other than your final exam practice question, okay? But if you do want to find something else, I think, let me double check, okay? I will now post a link under the description of this live streaming below. Let me see, where is it? So yeah, so keep asking questions, and I will see if I can post some sample questions, okay? I'm finding the link. Yeah, let me see if you have any questions. Do we need to know how to write down Excel formulas like in the midterm? I'm not pretty sure, but I think in your formula sheet you already have all the Excel functions, right? Given. Well, you better ask Boris, because I have no idea what's gonna happen in your final exams. I'm here today only for, only for exam preparation purpose, right? Can you show us the structure of the answer, like how to write the answer perfectly if you want to get full marking exam? Well, I think just follow whatever is in your slides, okay? Just follow the slides, or I think you also got the answer from you also got the answer from from Boris, right? The 2015. And Zeyu Cheng is asking how to calculate the prediction interval. Well, the prediction interval is for simple linear regression, it's just that complex formula, right? For multiple, you don't need to know it. It's a very complex formula. Right, I found the past exam questions here. Okay, I'll paste the link. I'll copy and paste the link in the video description and in the comment area, okay? Past exam paper example, okay? Right. Now, if you look at the video description, can you see the past exam paper example? Yeah, how to calculate the prediction interval. Oh, yeah, same. Okay, so, and also past exam paper example. I will post in the comment area below. Yeah, James W., I noticed your question. Can we have another revision for hypothesis testing and estimation? Yeah, if I got time, I can do another one next week. Is that okay? And yeah, I will post the comments here. No. The link is the 2012 paper interpretation, because 2012 is non-Excel. It doesn't involve any Excel operation, so it should be much similar to your this semester final exam. 2015 is Excel based exam, but look, they're all similar. Okay, all of them are similar. Don't worry. Oh, your exam is on Monday. Then we can do it on Saturday or Sunday, right? What about, let me see, Sunday and Sunday, Saturday. Saturday should be better, right? Yeah. I would say if I do it on Saturday or Sunday, okay? Probably Saturday evening. So, do you want the next one to cover 2015 paper interpretation? Like I take you through all the questions in 2015 semester 1 paper. At the same time, you're gonna know how do you apply all the knowledge in that paper and how to formulate your answer. What do you think? Okay, then that's the deal, okay? See you guys on Saturday. Okay? Yeah. I know you are expecting that. Okay? But before I do that, please watch the 2012, okay? Because I also attached the 2012 paper under the video description below that video, okay? So if you click on that past exam paper example and you click on that is semester 1 2018. So start reviewing that question, because I think 2012 is much more useful than 2015, because 2015, it's Excel based. All right. Right. Well, yeah. Me and my friend only knew this till now. You can still watch the recording after finishing this live streaming. All right. Okay, so if you don't have any other questions, wish you the best luck in the exams of this week. So yeah, so please put 100% of your energy and effort in the preparation of other units, and we'll start doing that on Saturday. Okay. All right. And make sure before Saturday, watch this video below, the past exam paper example. Well, I think I should write it down explicitly. And if you want to leave and have a rest, just do it, okay? I will do some changes, okay? 2012 past exam paper example video. Make sure you review this video before you attend the next one. And I will also how do I delete the comment? Anyway, yeah. So I'm now post the 2012 past exam paper example video, and make sure that you review this video before you attend the next one. Okay, cool. So that's all about today's live streaming revision. And thanks very much for your watching. I hope to see you in the next one. Bye-bye. 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 Okay. Yeah, you can see me, right? Bye.